But keep in mind, and this is why this failed. The original ride has a circular top, and then the little buckets, they hang down, and then the bucket is here. So you have something like this, the length of that string. We've got the radius of the ride, the mass of the bucket, the angle the bucket makes, and the rotational speed of the ride. Now, instead of asking you guys to do this and talk to your friends, and just let's work it real quick. It's not terrible. For example, there's only two forces here, tension and weight. If you didn't know you had to start here, we start here. And the reason we start here is because this is a circular motion problem. It has all the parts of circular motion. In fact, if you consider the fact that there's a piece of the tension this way and a piece of the tension this way, then you understand that this piece of tension is the one that's causing centripetal motion. And this piece of tension is the one that's balancing the weight of the ride. So T in the x direction equals MAC, and T in the y direction equals mg. Now, this does take work. There's stuff here, and I think you should be thoughtful of it, but I'm not going to sacrifice a lot of time for it. Theta is right there. Right, it has to be, because they have to be alternate interior angles back from geometry. That makes this T sine theta equals m omega squared r. I'm just going to go ahead and drop in centripetal acceleration in terms of the angular speed. And T cosine theta equals mg. Now we could eliminate T. Do you see that? I want a relationship that has omega and theta together, but I want to eliminate the tension. So I solve this for T, and I plug it in over there. And what we get is mg tangent theta equals m omega squared r. How we doing? That okay? Now here's what I wanted people to see and understand, that sometimes a simple idea becomes challenging. If this red line represents the center of the ride, then the radius of curvature has to be this r, which is a combination of this and whatever that distance is. Now that makes this harder, because these things aren't attached at the center. So this is going to be whatever r is for the ride, this r, plus L sine theta, because that's got to be this theta and this L. Yep. That's the distance from here to here. It's the radius of curvature of the ride occupant. This r is how big the actual attachment points are for the ride. So you put that together, and you find that the relationship between theta and omega is hard. It's not easy. And it's not obvious. I mean, if I want theta in terms of omega, it's going to take some more work, isn't it? And I'm going to get something that has both a sine and a tangent in it. And there's not going to be an easy way to tease out the angle. It doesn't feel like it's that complicated. But they gave this as an AP question one year. And the reason I bring it up is because in the AP question, they ask about this in a qualitative way. So this is the second FRQ. We have just finished the derivation for the velocity of the linear velocity of the wheel. Well, I don't know why I wrote it like that. And we have the angular velocity of the wheel. And we're asked, how long does it take for it to travel the distance L? Most students thought this was about the distance L, and it was not. This was about a time. I have two equations here that are functions that deal with time. What had to be done was you had to realize that rolling begins when that condition is met. L represented the length that the wheel moved through until that condition was met. This number was getting smaller all the time. This number started from 0 and was getting bigger all the time. We were looking for a moment where they came together. And we wanted to find out when that happened. So substituting this in for V and substituting this in for omega gives us a relationship that has time in it that could be solved to figure out when these two sides of the equation are equal. So V naught minus mu gt equals mu g over RT times R. We want to know when these two sides are equal. What T will make these two sides equal? So now I just solve it for T. Cancel the R's here, and I get V naught equals 2 mu gt on that side. And when I solve this for T, I get V naught divided by 2 mu g. This is how long it takes until the system is rolling. Interesting. If it starts off with a faster horizontal velocity, it takes longer. That doesn't surprise me. Has more speeding up to do and slowing down to do. I'm also not surprised that if the ground were stickier, the denominator would be bigger and the time would be smaller. So if the ground were stickier, it would take less time until rolling occurred. I'm not surprised by that. Go ahead. Because the moment these two things come into equality, the point on the ground is no longer slipping with respect to the ground. So suddenly the frictional force changes and is smaller. And what's funny is this happens abruptly. We don't have a lot of abrupt things like this in natural curves in nature, but if you were trying to study this, you would see a discontinuity in the graph of the velocity as it synced into place. But yeah, it's because the frictional force suddenly changes. Now, there's more to the problem. And a lot of students, even when they got here, couldn't answer the next question, which is, how fast is the wheel traveling when this happens? And we see this a lot. This inability to recognize that you're simply asked to find out a velocity. You create an expression for the velocity. You solved for a time, but without numbers, this alphabet soup just kind of messes with you. But we now have a time that we solved from two equations. We can plug it back into one of the equations for velocity. And it's funny, when you do, you find that the velocity equals v naught over 2. And you should do the substitution to see that, but it's not huge. Interesting. It was a ring, right? We just did a problem like that where it was a ring. We see that too. I don't think it would be a 2 if this were a disk or a hollow sphere or a solid sphere. I think that 2 is a product of it being a ring. And that's why it's half the speed. The next question was harder. They wanted an expression for L. You've got two choices. One of them's just mean, but you could do it. You could create another differential equation and split the derivative and find an expression for x and t, but set your limit for t to be here. Or you could realize that the acceleration is a constant and just say that delta x equals 1/2 a t squared plus v naught t. Use this for t and use your expression for acceleration, mu naught g. If you plug all that in, you get what L is. And if you're interested, when you plug all that in, this is what you get for L.